Thank you for your interest in on-site structural restoration methods for aircraft components. My name is Todd Sparks. I'm the principal investigator for this project and the director of research and development for product innovation and engineering. Pine is an additive manufacturing technology company in St. James, Missouri. We address metal additive manufacturing at every level with activities in process planning and simulation, feeding into and interacting with like AM system development. By creating our own tool ecosystem, we can create bespoke solutions to address very particular problems in AM. Historically, the bulk of our activity has been with directed energy deposition, which is the focus of this project. But more recently, we have done work in laser powder bed fusion processes and other adjacent applications which benefit from our prior experiences in AM. PMA 276 was our sponsor for this project. The problem, as it was articulated to me, was like a maintenance issue where when tearing down and building back the helicopters, the maintenance people might scratch or ding a component, which it wouldn't meet the fatigue requirements for smoothness of the surface, so they would have to polish. Then after so many passes of polishing out scratches, the part would be out of dimension and have to be replaced. So the main focus of what we're doing here is a system for restoring these components to their original condition without losing as much material, thereby extending their life. And the slide here says Type 6.4, but we primarily used 17.4 pH during this project. So one of the needs for this project is for the solution to be operable by people who are not necessarily additive experts. So this is where some of our simulation and CAM competencies come into play. So by running a thermal model alongside the process as it's running on the machine, we can do some parameter prediction on the fly, and that alleviates a lot of the expertise needed by an operator. So our solution to the AM repair problem, seen here as a system integrated into a CNC machine. So our primary effort is involved in the black rolling cart to the right of the CNC machine there. That's an additive manufacturing system controller. So that has all of the controls to handle all of the equipment that is not the CNC machine. So there's 2 lasers, 2 powder feeders, and several sensors. So this is all runs through an FPGA and a PC. So the primary operator interface is through a PC. The CNC machine is primarily in charge of all the timing in the system. We wanted to create a solution where we did not require special CNC machine controller modifications or even structural modifications to the CNC. So we have an off-axis optic system, which is the symbolized by the green box in the diagram there. So that points at a position below the spindle face. So we work on the tool axis. In the tool holder itself, we have a tool that dispenses powder. So powder feeds into that via the powder feeders. And so this lets us work within the same work volume that the CNC machine already would work with a normal drill or milling tool. So this tool can be removed and then return the CNC machine back to its normal like milling type activity. So that's part of the hybrid additive repair part. So we can do a surface prep or material removal by milling, switch over to add some material, switch back to milling and clean up. So when the photo was taken, we had yet to implement the automatic switchover. That's the thing that's still in motion for our phase 2 option. But the big deal here is the CNC machine is not special in any way. It is not modified. It just needs to be able to talk to the additive manufacturing system controller, which most modern machines have methods for network communication to talk to external devices. So this is no different than doing a robot integration or a third-party trunnion or something like that. So it lets us work with Haas for this first machine because they're American made, pretty robust, and relatively inexpensive, but it is applicable to robots or other CNC machines also. As you can see by the dates in this slide, we finished our phase 2 base last summer. By the time you listen to this, we should be in our phase 2 option. So as I mentioned before, one of our unique features is our ability to address additive problems at a lot of different levels. So in this case, we're integrating some of our CAM and simulation tools at the system controller level. So that lets us generate toolpath data on the fly from inspections done on the machine for a particular repair job, and use that data timed with a simulation that runs on the machine at runtime to do predictions of acceptable laser power inputs to produce a stable, steady state deposit microstructure. And so that also lets us generate parameters for how to operate our multiple laser system. So we do some integrated surface preparation work and that kind of stuff with a secondary pulse laser. And the state-based operation system plays into this as well. So the path generation created by a user, so that would be from some part on somebody else's site, their data, their information. We don't need to access that in order to actually help them work on a part. So if they have trouble with a situation, they can describe this to us. We can modify the technique portion of their CAM system and push that to them without needing to access their geometry data. So we just need a verbal description even of a problem situation, and we can work on a solution that is applicable to some sensitive data or proprietary information that shouldn't leave somebody else's site. So that's one of the reasons for this type of solution. So in our phase 2 base, we developed the additive repair system. We've been building 2 of them in parallel. So the primary task in our phase 2 option is to ship a machine out to Cherry Point and do some collaborative like application development with them. So the way it's set up, we can work on the technique side of the additive repair process without having knowledge of the actual parts they're working on. So we can push updates to on the technique side of it to their system for them and let them work, and they can describe problems to us and we can work on it. So we don't have to ever touch sensitive data to help them. So that's part of the intent of the system. I feel like this approach for a modular solution that we can put on, we worked with Haas machines for this project, but it's applicable to other CNC machine types or robots, just changing out one communications module. But so having a modular system, we can apply at different scales for different customers, and the state-based operations where we can support people and still respect their uh, IP rights on their geometry data, or their security on their geometry data. Feel that should be attractive to a lot of users, both government and non-government. So the AM repair system we created during the phase 2 base of the project, we demonstrated that it works. We did some demonstration repairs for the project itself. So we feel selling this as a system is an option, but in addition to that, as a modular creation done partially for our own sanity and additionally so we could sell bits and pieces of it to people who need that sort of equipment or competency that added to their systems. For some of the controls, we have been our own customers, so we're using parts of this project in two currently ongoing projects also. So we are our own customers in testing this too. And actually, we're working on the second iteration of the controls since the phase 2 base of this project. So that's still ongoing, still improving. Thank you for your attention. If any of this project seems interested to you in whole or in part, don't hesitate to contact me. Thank you.